Students, let us take up the next important concept, that is the magnetic field at a point due to a circular coil carrying current. That can be derived by using the concept of Biot-Savart's law. Yes, let us consider a circular coil which is carrying the current I, Let us say the radius of this coil is R. Then you can find what is the magnetic field acting at the center of the coil. The magnetic field acting at the center of the coil is given by mu naught by 4 pi into 2 pi n I divided by R. And also you can find what is the magnetic field acting along the axis of a circular coil. So, let us consider a point P on the axis which is at a distance x. Then the magnetic field at this point P is mu naught by 4 pi into 2 pi n I r squared divided by r squared plus x squared whole power 3 by 2. So, the magnetic field along the axis and the magnetic field at the center of the circular coil, you can see this formula. Clearly, by using this expressions you can conclude the magnetic field produced is maximum at the center of the circular coil and the magnetic field decreases as the distance increases from the center of the coil. So, in graphical representation, if you are going to show the variation taking the distance along x axis and the magnetic field along the y axis, at the center the magnetic field is maximum and as the distance increases the magnetic field decreases. Students, if you considered a circular coil having only a one turn, so considered a circular coil having only one turn, then what is the magnetic field at the center? What is the magnetic field at the center? You are going to consider only a one turn, only one turn is there in this circular coil. Then the magnetic field at the center of this circular coil is mu naught by 4 pi into, substitute n equals to 1 here. So, I can write that equation as I by r into 2 pi. Now, you consider the circular coil having only a half a turn. You considered a circular coil having half a turn, only half a turn. What is the magnetic field at the center? The magnetic field at the center of the coil having only half a turn is mu naught by 4 pi into I by r into pi. Just substitute n equals to 1 by 2 here, you are going to get this expression. Similarly, if I extend, now consider a small arc carrying a current I, then what is the magnetic field at the center of this arc? Let us join this, which is nothing but the radius of that arc, which subtends an angle at theta at the center. Then the magnetic field at the point O, that is at the center, is given by mu naught by 4 pi into I by r into this angle theta. So, magnetic field at a point due to a small arc, remember the formula, it is given by mu naught by 4 pi into I by r into theta. Now, let us take up the next concept, that is the magnetic field produced at a point due to a straight conductor. Students, the magnetic field at a point due to this straight conductor can be calculated by using Ampere circuital law. Here we cannot make use of Biot-Savart's law, because the conductor is not a small element, it is a very long straight conductor. So, for a very long straight conductor, to determine the magnetic field, we are going to use the concept of Ampere's circuital law, which states that the total line integral of magnetic field is equal to mu naught times the total current enclosed by the loop, that is nothing but the Ampere's circuital law. Using that Ampere's circuital law, you are going to determine what is the magnetic field at a point due to a current carrying conductor. Now, let us consider a very straight long conductor, which is infinitely long, which is carrying a current I. Then, the magnetic field at a point P due to this straight conductor, which is at a perpendicular distance of r. At this particular point P, the magnetic field is given by mu naught by 4 pi into 2 times of I divided by that perpendicular distance r. So, for a very long straight conductor, the magnetic field at the midpoint of that straight long conductor is given by the formula mu naught by 4 pi into 2 times of I divided by r. Similarly, if you want to calculate at one end of the straight conductor, the magnetic field is given by the formula B is equal to mu naught by 4 pi into I divided by r. At the midpoint, it is 2 times of I by r, at one end it is I by r. Let us extend this. This is the formula holds good for a very infinitely long straight conductor. Suppose if it is a short conductor of finite length, then what is the magnetic field at the point P here? We cannot use the same formula here. This is holds good only for a infinitely long conductor. For a finite length of the conductor, join the ends of the conductor to the point P. The perpendicular distance you can take it as r. Then the line joining from the ends of the conductor to the point P makes an angle alpha, and here the angle is beta. Then the magnetic field at this point P, is given by mu naught by 4 pi into I by r into sin alpha plus sin beta. This is the formula for the magnetic field at a point due to a straight conductor of finite length. Suppose if you are extending this, if I considered a square of side A and carrying the current I, then what is the magnetic field at the center of the square? What is the magnetic field at the center of the square which is carrying the current I? You can find what is the magnetic field at the center of the square using this formula. Now, let us consider only a one side of the square which makes an angle 45 degree at the center of the square. The perpendicular distance is equal to a by 2. Then you can find what is the magnetic field here. Alpha is 45, beta is 45, therefore, sin 45 plus sin 45, that is 1 by root 2 plus 1 by root 2, that is nothing but root 2. So, the magnetic field is mu naught by 4 pi into I divided by the perpendicular distance, that is a by 2, into this bracket term, that is root 2. So, it becomes mu naught by 4 pi I by r into root 2, r can be replaced with a by 2, so it becomes 2 root 2. So, what is the magnetic field for one side of the square? Mu naught by 4 pi I divided by side of the square into 2 root 2. That can be extended for the 4 sides. So, multiplied by 4. So, the net magnetic field at the point O, that is at the center of the square, is equal to mu naught by 4 pi into I divided by side of the square, that is A into 8 root 2. So, please try to remember this formula, students. If they are asking to find what is the magnetic field at the center of the square, straight away you use the formula mu naught by 4 pi into 8 root 2 times of the current divided by the side of the square. In the same way, you can extend for a equilateral triangle. If you are going to consider an equilateral triangle of side A, then you can find what is the magnetic field at the center O. Let I is the current flowing in the equilateral triangle. Then the magnetic field at the center of the triangle is given by, in the same way you can proceed, you are going to get mu naught by 4 pi into 18 times of I divided by the side of the square. So, for equilateral triangle, the magnetic field is mu naught by 4 pi 18 times of I divided by side. For the square, remember, it is mu naught by 4 pi 8 root 2 times of I divided by the side. So, this is the formulas for the magnetic field at a point due to a straight conductors. Now, let us go to the next concept, that is the magnetic field at a point due to a solenoid and the toroid. For solenoid and toroid also the magnetic field can be arrived by using the concept of Ampere's circuital law. Now, what is the expression for the magnetic field at a point on the axis of a solenoid? Suppose if I am going to consider a solenoid which is having a cylindrical coil, where we are going to wound with some number of turns. Let us say it is wounded with n number of turns. Let small l is the length of the solenoid, that is cylindrical coil. This each turn is carrying a current I. Then the magnetic field at a point on the axis of a solenoid. The magnetic field at a point on the axis of a solenoid is given by mu naught into small n into I, where I is the current flowing in this coil, small n represents the number of turns per unit length, that is n by L into I, where L is the length of this solenoid and n is the number of turns, I is the current flowing in the solenoid. Then the same expression can be used for toroid. Toroid is nothing but the solenoid which is endless. So, endless solenoid is called as the toroid. Just you bend that solenoid in the form of a circle, that gives the toroid. Then the expression for the magnetic field for the toroid also remains same, that is mu naught into n into I, where small n represents the number of turns per unit length. And you can see the graphical variation of the magnetic field in the case of solenoid. L is the length taken along the x axis, magnetic field along the y axis. Certain distance the magnetic field is not going to change, it is not going to vary for a certain length. From that the magnetic field start decreasing. This is the graphical variation for the magnetic field versus the distance in the case of solenoids.
ಡಿಯರ್ ಫ್ರೆಂಡ್ಸ್, ನೀವು ದಿವಿಗೆ ಯೂಟ್ಯೂಬ್ ಚಾನಲ್ಗೆ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿ, ನಿಮ್ಮ ಫ್ರೆಂಡ್ಸ್ಗೂ ಹೇಳಿ, ಇದೇ ಥರ ನೂರಾರು ವೀಡಿಯೋಸನ್ನು ಫ್ರೀಯಾಗಿ ನೋಡಿ.